All right, lesson number 2 in Calc BC is all about parametric equations. Parametric equations are tough at the get-go because you've got to fight through a definition. But once you fight through the definition, it's really not too bad. So what I'll do is I'll show you the definition, then we'll talk about what it means in English. So let's pretend that x and y are given as functions. This lingo right here just means that x is some function of time and y is some other function of time. Generally, we think of t as time because that helps us visualize what's going on physically. So x is some function of t, y is some other function of t. Of course, f and g could be the same function, not a big deal there. So if x and y are given as functions of t over an interval of t values, and that interval can be a closed interval or an open interval. It can run from 0 to 1 only. It could run from 0 to 10. It can run from -5 to 5. It could run from -infinity to infinity over any interval of t values. Then the set of points x, y, defined by these equations, is called a parametric curve, because t is called the parameter. T is the thing that we control. If you're into science, biology, chemistry, physics, t is the independent variable. X and y are both dependent variables. So what I want to do is I want to show you what it looks like. When we graph a parametric curve, x and y are both given to us in terms of t. So maybe x is the square root of t and y is t for t greater than or equal to 0. Maybe that's our interval. It's a half-open interval, closed on the one end, open on the other. So I want to get a picture of it, but to get a picture of it, I've got to have an idea of what the values are, where the points are. Now, when you were in 9th grade, you would set up a t-bar chart like this, and you would have x and y, and you'd make some x values up and some y values up. Well, here, to give us an idea, we'll have a txy chart. And so we'll pick certain values of t, maybe 0, 1, 2, 3, just to get a sense. And x and y are determined by that. So if x is 0, then x is the square root of 0, and y is 0. In fact, with y being t all the time, the y column is easy to figure. X is the square root of t. So we've got square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. And if we plot those points, oh boy, this should be fun. 1, 2, 3, 4, 1, 2. If we plot those points, 0, 0, 1, 1, 2, 4 is easy. The others get tricky. You get a curve that looks like, oh, really? Really? Well, that's right there. You get something that looks like that. Mind you, the parametric curve moves in that direction. If we imagine that t is time and Pete the particle is moving over time, he starts at the origin. The origin is called the initial point. There is no terminal point because t is allowed to grow forever. Now, of course, that picture looks very familiar to us. That picture looks like y equals x squared, and that should not surprise us, because in this equation, if we were to solve for t, x squared is equal to t just by squaring both sides. But wait a minute, t and y are the same thing, so we would expect that this graph would look like y equals x squared. Why don't we see the left half of the parabola? Because t is only allowed to be non-negative. So if you have a parametric curve, a set of parametric equations to graph, you can use a txy chart and graph the sucker. by just plotting values. Not too bad. Of course, there are times when it gets a little bit more difficulter. Oh, example 2. Let's graph x equals 4 cosine t and y equals 4 sine t for t between 0 and 2 pi inclusive. Well, we could graph a series of points, I imagine. Oh, really? I did that? Really? And I was recording. So, I mean, we could pick some points along the way, I imagine. And then you would have to remember what the cosine and sine of those things are. And so you remember that the cosine curve starts high, like too many of your friends, and it ends high. And you would have to remember that the sine curve starts and ends at the midline, hits the midline halfway, and then goes up and down. And so you've got some points to plot. You've got 4, 0, 0, 4, negative 4, 0, 0, negative 4, and then back where you started. So the question is, what does it look like in between? Is it a square? Is it a kite? I mean, what is it? So luckily, we have the help of our graphing calculator to get us through this. In our graphing calculator, if you were to hit the mode button, and the mode button is this button right here, you can see on this line that your graphing calculator can graph in several modes. Mostly you've graphed in function mode because that's what we've been graphing in forever. But you can also graph in parametric mode. And so when you graph in parametric mode, when you hit that y equals button, function 1 has an x component and a y component. And so I type 4 cosine t and 4 sine t. That's not too bad. Now I'm going to hit window just to see if I've got a decent window. I'm supposed to graph t values between 0 and 2 pi, and sure enough, that's what I've got. I've got t values between 0 and 2 pi. My x min and my x max are appropriate, negative 10 to 10, that's the standard viewing window, and so I hit graph and I get a picture. It looks like that. And I can trace that picture, and it will keep track of my t values and my x values and my y values as I go all the way around the curve. The question is, what kind of curve is it? And the answer is, I'm not sure. So what I'm going to do is I'm going to square up the viewing window so that my negative 10 to 10 up and down looks the same as my negative 10 to 10 going across. That's the best way I know of to graph. And sure enough, you would think that this thing is a circle, and it is. So I'm going to take a picture because it lasts longer. I'm going to slide that right into our notes. Oh, wow. How do you like that? That's the picture. I mean, when we connect the dots, we are getting a circle. Now, how did we know we were going to get a circle? Well, because I know something you don't know. I know that cosine squared t plus sine squared t from everything I learned in Algebra 2 is, I can hear you saying it at home, 1. Well, from the top equation, I know that cosine t is x over 4, and sine t is y over 4. So I know that I've got x squared over 16 plus y squared over 16 is 1, or if you like, x squared plus y squared is 16. That's a circle centered at the origin, radius 4. By the way, radius 4 because, you're never going to believe this. Gosh, I hope that makes sense. Gosh, I hope that makes sense. So if we were to change the 4s to 6s or 2s or 8s, we would change the radius of the circle here. We would change that radius to 6 or 8 or 2 or whatever it was. Okay? Okay. Oh, the interval matters. What if we were to change that interval? What if we were to graph instead from 0 to 4 pi? Well, you'd have to, wait a minute, that's the same picture. How can that be the same picture? Well, that can be the same picture because when we trace, we follow the periods of the sine and the cosine function. And every 2 pi, we're right back where we started, and we just pick that right up all over again. So if we go 0 to 4 pi, we get 2 complete revolutions, starting at 4, 0, ending at 4, 0. If we were to graph from pi to 3 pi, we still get a full revolution, but notice it started over here. This is the initial point. And we get 1 full revolution because our interval of t values would include 1 period of the graph, and that's 2 pi. So far, okay? Okay. Awesome. In the privacy of your own home, you should probably consider x is 2 cosine t and y is 3 sine t for t running from 0 to 2 pi. Oh, we can consider that together, can't we? We can do that. That's a 2 cosine t and a, oh, really? Really? I did that? Sorry, folks. And a 3 sine t, and we'll run that from 0 to 2 pi. What is that? What is that? It looks to the untrained eye that this is not a circle, but a squished circle where that's 2 and that's 3. Interesting. If you're keeping score at home, this thing is what we call an ellipse, but it's impossible for me to demonstrate for you how this 2 and this 3 play into that picture. That is a great mystery. We are never going to unravel that. Oh well. Hey, one more. One more to graph. Let's graph x is 3 minus 3t and y is 2t for t between 0 and 1. T between 0 and 1. If I made a txy chart, it's pretty straightforward that if t is 0, x is 3 and y is 0. If t is 1, x is 0 and y is 2. So we've got, really, I did that? We've got the point 3, 0, and we've got the point 0, 2. And the question is, how do you connect them? Is it a parabola? Is it part of a circle? Is it a line? What is it that connects them? So what I'd like to do is I'd like to use a time-honored algebraic technique. I would like to solve for t in one of the equations and substitute it into the other. That's what I'd like to do. So I'd like to solve for t here and stick it there. Well, that's not too bad. If x is 3 minus 3t, then x minus 3 is equal to negative 3t. So t is x minus 3 over negative 3. And then we just stick it so that y is 2t. Right? And by my count, that's the equation of a line. In fact, specifically, that's the line y equals negative 2/3 x plus 2. Now the whole line would look like this. This would be the whole line, but we don't want the whole line. We want only the part of the line that starts at 3, 0 and ends at 0, 2, because our interval of t values was held from 0 to 1. We have to start when time is 0 and stop when time is 1. And furthermore, the line segment has a direction to it. It's almost like a vector in that regard. It is a directed line segment where t equals 0 is at 3, 0, and t equals 1 is at 0, 2. The line segment starts at 3, 0, it ends at 0, 2. It's got an initial point and a terminal point. How am I doing so far? Not too bad? Not too bad. Awesome. Cool. So in our class time, we'll talk about how to parameterize line segments. That will be the way we'll piggyback on this into a lesson, and then we'll dive into some practice together so that we all understand what we're graphing. Side note, there's a historical note on page 33 of your textbook about Maria Agnesi. The Witch of Agnesi is a great story. You really ought to read about it. Maria Agnesi, as we all know, is the first woman ever to do math. So there you go. That's lesson 2. Hope you enjoy. We'll see you tomorrow.